Hi everyone, today we're talking about the graph of a quadratic equation in the form of y equals ax squared plus bx plus c, where a is greater than 0. So what that means is we're looking at specifically the situation where the number being multiplied by the x squared is a positive number. A is greater than 0. Okay, so in our previous lesson, we learned about the graph of linear functions, which follow the format y equals mx plus b. So in that situation, we are going to create a straight line, and the highest power of x is 1, right? There's no squared there. X is to the power of 1, which disappears because we don't really go around writing x to the power of 1. We just write x. Okay, so today we're going to try and see what the graph of a quadratic equation is going to look like. So try to think to yourself now, try and predict what the shape of that graph will look like before we start. Okay, and then to review, the quadratic function or equation is going to follow the format y equals ax squared plus bx plus c. And remember, a, b, and c are basically place values for constants or just normal numbers that aren't being multiplied to a variable. And keep in mind that we're thinking about situations where the a value, the number being multiplied by x squared, is not equal to 0, because obviously if it's equal to 0, it's going to cancel out and it's going to get rid of that term, right? So not looking at 0 as a possible constant here. Here are some examples. Y equals 2x squared plus 3x plus 4. Y equals x squared minus 3. So the middle term can disappear, but we really are looking at a quadratic equation, what its graph will look like when we do still have that square term. So y equals negative x squared minus 6x plus 1. Those are all quadratic functions. So very important that that first term with the x squared maintains that original shape. Okay, so we are going to be exploring the graphs of quadratic functions. And remember, for today's lesson, just only when the coefficient of x squared, that number being multiplied by x squared, is positive. So a is greater than 0. For negative values, we'll save it for a different lesson. Okay. So we will start off now with just our basic y equals x squared. We don't have the bx, we don't have the c. We're just looking at what y equals x squared will look like on the graph. Okay, so I'm going to start off by making up some values for x. I am going to start with -2, then -1, 0, +1, and 2. So I can kind of chart its change with different values for x, and also look at how it's behaving in the negative x values when x equals 0 and in the positive areas. Okay, so according to my equation, y equals x squared. So when x equals -2, I'm going to go ahead and square my x to figure out my y value. Okay, so this is square just means to multiply by itself. So this is -2 times -2, which is going to cancel out to become a +4. For -1, when my x is equal to -1, x squared, so those two are multiplied by each other. Negative times negative positive, 1 times 1 is 1. For x equals 0, 0 times 0 is still equal to 0. For x equals 1, remember x squared multiplied by itself, 1 times 1 is 1. And for the next one, 2 times 2 is equal to 4. So you'll notice, and let me go ahead and rewrite these as coordinate points, coordinate pairs, so that we can graph these. But you'll probably notice that there is a pattern, right? The y value ends up being the same whether it is a positive or negative x value. So before we even graph these points, go ahead and just kind of make a prediction in your head of what do you think this graph is going to look like? Because we do have y values that are repeated. Okay, let's go ahead now and plot these. -2 and 4. So I'm finding -2 on my x-axis. Then I'm going up to connect it to y equals 4. Next is -1 and +1, finding -1 first, and then flying up to 1. Okay, and then 0, 0 is in the origin. Now, here's where it gets interesting. Then I'm plotting 1, 1, +1, +1, and then 2, +4. Well, you look at that. Well, first off, it's not a linear, it doesn't look like a linear equations graph, right? It is not a straight line. It's going to curve, and let me try and be as accurate as possible when I'm drawing this. Okay, so it's going to curve up. Hopefully your prediction was right. And why does it curve up? Well, let's look at our values. We went from 4, then down to 1, and then we went to the origin, and then we shot right back up, and we had to match those same values, right? Because the negative times negative was positive, positive times positive was also positive. So basically we have a symmetrical line here, right? And this line actually is called a parabola, Parabola, okay, because it curves. Now, does it have a constant rate of change? It does not, because at first your slope is negative, it's decreasing, then it kind of levels out for the curve, and then your slope goes back up and it's increasing. So this is not a constant rate of change. Okay, so quadratic graphs do not give you a constant rate of change, and they have a curve because of that x squared. That x squared forces your x to multiply by itself, so then your negative x's will give you a positive answer for y, and vice versa for your positive. Positives will also match that value. So it's going to curve back up, and it's going to create this line of symmetry here where you can fold it over and it matches. Kind of cool. All right, so make sure that's in your notebook. And we're going to move on. We're going to continue to explore some other quadratic equations. Here's our first question we want you to explore. How do you think the a value, remember that's the constant, or that's the coefficient that's being multiplied by your x squared. How does the a value change your quadratic graph? So now we're kind of playing around with our a value of 1/2 and an a value of 2. One is a number that is less than 1, and another is a number that's greater than 1. So first, make a prediction in your head. How do you think that's going to change your quadratic graph? We already know it's going to be a curve, right? A parabola. But how do you think changing your a value like that, using a fraction versus a number greater than 1, is going to further change your quadratic graph? Now we're going to cheat a little because we have a lot of different quadratic graphs to explore, so we want to save a little bit of time. I went ahead and I inputted the graphs that we're going to explore into Desmos so that we can, again, save a little time. Remember that we are trying to figure out how changing that a value, the coefficient in front of the x squared, is going to change our graph. Here is our original y equals x squared. Remember, we have our parabola. So let's go ahead and see how the 1/2 x squared will change our graph. So we're going to turn that on. There you go. That's the red one right there. So go ahead and note to yourself what you notice. I noticed that it got wider, right? Which is interesting because when you think of a fraction, you think of smallness, but it actually got wider. So now think to yourself, if I were to select the y equals 2x squared, how do you think that's going to change your graph now compared to your original green y equals x squared? Okay, there you go. So the 2x squared actually made it more narrow, which is interesting. All right, let's go ahead and put that in our notes. So the 1/2 x squared made it a bit wider. I'm going to go ahead and exaggerate it. And then the 2x squared made it more narrow. Okay, and we're just sketching it. Okay, we don't need it to be completely accurate because we're just trying to figure out the overall pattern. And then we have here what the values were for x and y for our original y equals x squared. Let's go ahead and figure out why these changes happened. Why was it that multiplying by an extra half made it wider, while multiplying by a 2 made it more narrow? Okay, so let's go ahead and look at the 1/2. We're taking our y value and we're multiplying by an extra 1/2. Well, what's 4 times 1/2? That would be 2. What's 1 times 1/2? That would be 1/2. I'm going to put 0.5. And then, this one will still say 0 because anything times 0 is still itself. 1 times 1/2 is 1/2. Remember, these are just going to repeat, right? Okay, so it looks like instead of going from 4 down to 1, and then up to 1 and back to 4 again, we now have a 2, -2, and a +2. Just going to go ahead and sketch it real quick. Okay, we have a -2 and a +2, and then down to a -1 and a 1/2. See how that kind of widens it a little, right? So basically, the reason why it's wider is because we have lower numbers, right? Our original one reached up to 4, which is all the way over here. So that's why it was a little more narrow. For when you're having the numbers, you're going to create smaller numbers, so then it's going to create more of a wider bowl because the numbers are lower. Okay. Conversely, now if we were to look at I accidentally erased this. If we were to look at multiplying by 2, we're going to take all these and multiply by 2. You're going to end up with 8, 2, still 0, 2, and 8. Okay, remember when you have higher numbers, it's going to be really narrow because it has to reach all the way up there. Okay, so we have -2. That has to pair up with an 8. 1, 2, 3, 4, 5, 6, 7, 8. So it's going to go all the way up there, and then -1 pairs up with 2, and then it reaches down. Woo. It's super narrow because we have these really high numbers. Multiplying by 2 made our y values really, really high, really big numbers, so it had to reach all the way up, which is then going to narrow our parabola. Okay, so let's add that to our notes, okay? So that we're not just writing wider or narrow. We want to also figure out what about the numbers, the x and y values, made it that way. Okay, so for a number or a value that's less than 1, it is wider because the y values were lower. For 2x squared, this was more narrow because, remember, our y values were higher, so it had to reach higher. So the graph had to stretch and reach higher. Okay, because then multiplying by 2 instead of a 4 created an 8. So it had to go all the way up to reach that 8. which makes a lot of mathematical sense, right? And now why are we doing this? So that we can then predict before we even graph how our graph is going to look like and kind of check our logical sense when we graph our graph, right? See if it actually makes mathematical sense. All right, let's explore some more. So our next exploration question asks us now to look at the C value. Remember, the C value is what's being added at the end to your quadratic equation. Okay, so we're going to look at y equals 2x squared plus 1 versus y equals 2x squared minus 3. Notice how they both have the a value of 2. So is your graph going to be really wide or really narrow compared to your general x squared graph? If you said narrow, you are correct, right? Because multiplying by 2 in the beginning is going to create bigger y values. So it's going to have to reach really high for the big numbers. Okay, so in general, our graphs are going to look like this, kind of narrow, not your generic one, which is the x squared. Okay, so let's take a look at Desmos now to figure out what changing the C value, we have a +1 and a -3, what that will actually do. And go ahead and make your predictions before we do so. All right, so we're going to go ahead and clear the narrow and the wide graphs from our change in A value. And now we're going to look at how the C value changes. So we still have our green generic x squared graph. And we're going to add on now this one. Uh-oh, it's another green. Go ahead and see, what do you think happened there? Original and new. And now we're going to look at the 2x squared minus 3. Ooh. Okay, so think to yourself, how did changing that C value change our graph? Well, you probably noticed that it shifted its location, right? Our original one was just x squared, added a 0, technically, no C value. And now when we subtracted 3, did it go down 3 steps? 1, 2, 3. It did, right? And then +1 shifted it up 1. Okay, so let's go ahead and add that to our notes, that changing the C value actually shifts it up and down. Okay, so we're adding to our notes. I'm just going to do a quick little sketch that adding 1 shifted it up 1, and then subtracting 3 at the end shifted it down 3. And I can even show the scale so that we can see that. Remember, it's just a sketch though. Okay, so it went up 1 unit, and let's be specific, on the y-axis, right? And this one went down 3 units on the y-axis. Okay, that makes sense too, right? Because previously we talked about how the b value in a linear equation was the starting point on the y-axis. So, and that b value was being added in at the end of a linear equation, right? Because it was y equals mx plus b. So the c value is kind of like that b value in your linear equation, where it's kind of showing you its position on the y-axis. So a lot of similarities between the quadratic equation and the linear equation. This c value is kind of like your b value in the linear equation. Interesting. Okay, let's move on to the next exploration. How now do you think adding or subtracting to your x variable will change the quadratic graph? So what we mean by this is adding or subtracting from your x value, and that's before you square it. So notice how we have parentheses here, okay? So think to yourself, try and make a prediction before we then hop over to Desmos and actually see for ourselves the results. All right, let's take a look. Let's erase these. We have our generic x squared. Let's see what adding 1 to our x value, that's before squaring it, will do. Ooh, interesting. It shifted it. To the left one. It's a +1, which, normally you would think would move towards the positives to the right, but it actually shifted it to the left. So predict in your head now what x minus 1 squared will be. If you said it shifts to the right, you are correct. So it's like the opposite. Kind of reminds me of your, when you were solving the answers for a quadratic equation, right? It was, if you set x minus 1 equal to 0, right? Then the answer at the end was the opposite sign, which was a positive. Kind of reminds me of that. It's like you have to remember it's the opposite. And it has like the same binomial setup. So I wonder if it has anything to do with that. So interesting. So now we're looking at movement left to right on the x-axis as opposed to shifting up and down on the y-axis. Interesting stuff. Okay, let us add this to our notes. So again, I'm just going to do a quick sketch. X plus 1 squared. Remember, it's +1, so it actually moved in the opposite direction. It shifted over to the left 1 spot. And for x minus 1, it shifted over to the right towards the positives 1 spot. Okay, so we're going to say moved 1 unit to the left on the x-axis. And over here, moved 1 unit to the right on the x-axis. Okay, interesting. And then I have the graph of your original y equals x squared so that we can see what is going on mathematically. How did that actually happen? Okay, so over here, instead of 4, we're going to have a different value now, right? Because instead of x squared, the -2 multiplied by -2, we have x, -2 plus 1 would be a -1 times -1, which is a +1. Okay, and then for our -1, it'll be -1 plus 1, which is 0. 0 squared is still 0. There it is. So shift it over, if you notice. Instead of the middle term being on the axis, it's now shifted over to this earlier point, if you will, x value, shifting over to touch the 0. So that's how that happens, because you added 1. You changed the value now before you squared it. Very interesting. All right, last one then. See if you can predict the graph for y equals x minus 1 squared minus 2. How would that graph look like? Got a lot going on here. Okay, let's take a look. Let me go ahead and delete these. Here's our generic y equals x squared. Let's see if your prediction was true. Here's the graph for y equals x minus 1 squared minus 2. So it was a -1, so then we know it's moving to the right 1 spot, okay, because of this. And then it was a -2 for our c value, so that one just does a straight shift down 2 units. So that's why it ended up over here. Hopefully you got that correct. Okay, so let's go ahead and write down what that graph kind of looked like. It went to the right 1 unit, and then it went down 2 units. And so then we can kind of sketch what that looked like. Right 1 unit, and then down 2. So like this. And it wasn't, necessarily narrow or wide. All right, and then the last thing that this problem is now asking you is how can we rewrite this equation in simplified form, right? So this equation, y equals x minus 1 squared minus 2, can actually be written in a different format. We can multiply out the x minus 1 binomials. So that would become x squared minus x minus another x plus 1, because negative 1 times negative 1, which simplifies to x squared minus 2x plus 1. So this would be x squared minus 2x plus 1, and then minus 2. So this equation is really x squared minus 2x minus 1. These two are the same. Okay, so this is why, breaking it down into its kind of factored form can sometimes actually help us in a different way compared to its simplified form. And we'll talk more about that in the future. All right, so some things to summarize and add to your notes. First that we talked about was that when a is greater than 0, the graph opens upward and it's called a parabola. Secondly, the graph has a lowest point. It is called a minimum point, which makes sense, right? It's the lowest point, the minimum. There is a vertical line that goes through the minimum point, and that is what we call the line of symmetry, because everything on the left-hand side is basically identical to everything on the right-hand side. We can kind of fold it over like a mirror. That's the line of symmetry. And then the smaller the numerical value of a, remember with the multiplying by a decimal or a fraction, the wider the graph is going to open upwards because you're creating lower or smaller values. And then, vice versa, the bigger the number is for the value of a being multiplied by x squared, the more narrow it'll be, because then you have really high values that you have to reach all the way up and stretch. Okay, and lastly, the graph may meet the x-axis at 0, 1, or 2 points. Okay, but it's always going to meet the y-axis at only 1 point. So what do we mean by the graph meeting the x-axis at 0, 1, or 2 points? Here's where it looks like where it's meeting the x-axis at 0 points. Boom, it kind of hovers above. Meeting at 1 point would be like if it just kind of meets at 1 point, touches the minimum point. And then it could also meet at 2 points, kind of like this. Yeah, because it's kind of shifted all around. But in each case, the graph only touches the y-axis at 1 point. Here eventually, when that one's extended, and here. Okay? Here's example 4. A horizontal bridge is 20 meters long and it is supported by a suspension cable. The height, y meters, of the cable over the bridge at a distance x meters from one end of the bridge is given by y equals 0.03x squared minus 0.6x plus 5 for the values of x that are greater than or equal to 0 and less than or equal to 20. You need to draw the graph for that equation, then find the height of the cable at one end, and then state the line of symmetry for the graph, and find the minimum height of the cable above the bridge. Okay, so you basically have a bridge, and it has a suspension cable. You've seen bridges like this before, right? Like the Golden State Bridge is kind of like this. All right, good news is since there's decimals here, we can definitely use Desmos to make our lives a little easier because it's going to be less accurate if we do this by hand. So we're going to skip over to Desmos right now. Okay, here is our graph on Desmos for y equals 0.03x squared minus 0.6x plus 5. Let's see what the problem is asking us. Part B says find the height of the cable at one end. Okay, so at one end, that'll be where x equals 0, because x is the distance from one end of the bridge. Okay, so x would equal to 0 and then our height would be 5. So that is the height of the cable at one end. And then state the line of symmetry for the graph. Well, it looks like it's right here. So this line of symmetry would be x equals 10. And then find the minimum height of the cable above the bridge. Okay, remember our minimum is where it curves. So the minimum height would be y equals 2. So minimum height is 2 meters. That's it. Your graph tells you all the information that you need.